So again, we're going to use technology to simulate the sampling distribution for proportions, so that again, with a click of a button, we can look at lots of sample results very quickly to see if we can generalize or make any generalizations about what happens with this sampling distribution, kind of like we did in the last section. So we're going to open StatCrunch and we're going to go back into the applets for sampling distribution. But in that pop-up window this time we're going to choose binary, meaning that we have each of our individuals, we have just two categories we're placing them into, which is what we have for the binomial distribution. And for this particular one, they told us 60% of all students pass, so next to P we're going to put in a 0.6 and then click Compute. All right, so let's go into StatCrunch and do that. So again, we're going to click Applets and we're going to go into Sampling Distributions. All right, in the last unit we looked at the uniform distribution. This one we are going to click binary, and in here for the value of P we're going to backspace over 0.5 and change that to be 0.6, and then we're going to click Compute. Alright, so again we have this axis of zeros and ones, so keep in mind we really have qualitative data, so it's just demonstrating that we've got 60% of the students over here in the passing group and 40% over here at 0 in the failing group. Okay. So again, in here we are going to set our sample size, and then again we can click how many times we want to see those samples generated, and on this bottom graph here that we see, it's going to graph those sample proportions for us, which will be a number between 0 and 1. So now the next three pictures are each going to show the results of approximations for the sampling distribution of the proportion once when n is 10, and then I'm going to walk through that again when n is 50, and then we're going to do that simulation one more time with a sample size of 100. In each case, I'm going to generate 5,000 samples of that specific size. So keep in mind that in all three cases, P is going to be 0.6. So the population percentage of students who pass is going to be 60%. But when we randomly select a group of 10, or randomly select a group of 50, or randomly select a group of 100 students and ask, what percentage of that group passed, it's not always going to come out to be 60%. There's going to be some fluctuation in those sample percentages. So this sampling distribution of the proportion also has a mean and a standard deviation, and so we're going to get some new symbols for those as well. So keep in mind that the subscript designates the random variable. So the mean of a distribution, we use the symbol mu for that, and now our new random variable is p hat. So we're going to get mu sub p hat. And the standard deviation for a probability distribution, we use sigma for that. And again, the subscript now, the new random variable is p hat, so sigma sub p hat. So these are our two new symbols for this section. Okay, so now again, we're going to go into the applet to generate, and again, this one where I've generated, this one n was 10, and I'm going to generate 5,000 samples. And again, this mean here is going to be the mean of the distribution of all p hats. Okay, now we didn't take all possible samples of size 10. We're going to take a lot here in a second, 5,000. So again, mu p hat came out roughly 0.5968, which you should notice is kind of close to 0.6. Okay, and the standard deviation of this distribution, so sigma p hat, can be approximated from these 5,000 samples with the number 0.1545. Okay. Then we're going to run through that simulation again, and we're going to change n to 50. We're going to compute 5,000 samples, and again, these are going to give us approximations for mu p hat and sigma p hat. And then finally, we're going to run through that simulation one last time with a sample size of 100. Again, we're going to generate 5,000 samples. And again, we're going to get yet a different approximation for mu p hat and sigma p hat. All right, so let's go into StatCrunch, and we're going to start with this first simulation when n is 10. Now keep in mind the random sample, so as I generate something on my screen and you should be generating something on your screen, you're not going to get the exact same thing that we see pictured in the textbook here because they're random samples. They're going to be different due to sampling error. All right, so in here for our sample size for this first one, we're going to delete that 2 and put in 10 for our sample size. And again, we're going to generate a sample, 5,000 samples. So we're going to hit this 1,000 5 times. So there's 1,000 samples, another 1,000, another 1,000, another 1,000, and yet another 1,000. So we can see down here the total number of samples that we've generated are 5,000. Each sample size was 10. What's displayed on the middle graph is the last, so like the last sample that was generated, 70% of those kids passed. Okay, and again down here we can see an estimate for mu p hat is 0.6004. Okay, it does not match the 0.5968 shown in the textbook because again it's based on random samples. But again, both values are very, very close to 0.6. And the standard deviation here is 0.1546. Again, different from the one in the textbook, which is 0.1545, but they're very close to each other. All right, so now we're going to reset this. And we're going to do the simulation again for samples of size 50. So we're going to delete 10 and change that sample size to 50. And again, we're going to generate 5,000 samples. So this is like we asked 50 third graders in Illinois, did you pass or fail? And we recorded the percentage who passed. And we did that 5,000 times with the click of a button with the simulation. Saves a lot of time. All right, so again, we can see our number of samples here is 5,000. Each of those samples was a size 50. What's displayed on the middle graph is just the last sample that was taken, where 56% of those students passed the reading exam. And again, we have our approximations for mu p hat at 0.5985 and for sigma p hat of 0.0689. Again, they do not match the values that are given on the simulation that's captured in the textbook because, again, they're random samples. But again, we should notice that this mean is very close to 0.6. The standard deviation is smaller than the initial standard deviation we started with, and it's smaller than the standard deviation that we had when n was 10. Okay, so once again, we're going to reset this, and we're going to change this sample size to 100 and generate 5,000 samples again. 1, 2, 3, 4, 5. Okay, so again, we should notice this curve down here. Although the initial ones looked kind of bell-shaped, they had a lot of gaps in them. Okay, here's we're looking at these bell-shaped curves, and we're finding that those gaps are being filled, and we're getting a much prettier bell-shaped curve each time as we've taken larger and larger sample sizes here. All right, so now let's go back to the page and look at some of these numbers. So again, this first graph, again, we're starting to see this look kind of bell-shaped, but again, lots of gaps between those bars because we had kind of a small sample size, and so the only proportions that were even possible were things like 0.1, 0.2, 0.3, 0.4, and so on. As we increase our sample size here to 50, again, we still see some gaps in the bars. Again, it's looking very bell-shaped still. Okay. By the final graph here, again, we're seeing those gaps really starting to fill in, and again, we're seeing this bell-shaped curve. So one thing we should notice between these three curves is all three of them were centered in approximately the same place at 0.6. But those curves were getting more and more spiky and taller in the center and not as much spread. Okay, so this first one is kind of spread out. That standard deviation was 0.145. The next one when the sample size was 50. Okay, this one's more concentrated near 0.6, and that standard deviation now is only 0.069. And in the final simulation we did where n was 100, again, it's really concentrated here near 0.6, and that standard deviation for that graph was only 0.0497.